Hey, we're going to do the quick version in case you missed anything this week. And get right to it. We've been going over this week atomic structure. So where we started was to look at what we consider to be the most important parts of the things that make up the atom. So what we know, what we believe about our world now is that everything is made up of atoms. Atoms are the fundamental building blocks of everything. There are things smaller than an atom, but we tend to say start at the atom and saying that this is the 100+ items that make up all the things that we know about around us, or that we could actually put together in a lab. So our atoms have some subatomic particles, some things that make them up. So these are our protons, our neutrons, and our electrons. And each of these contribute different things or different characteristics to the atom. Some of the things that we know about this, they have different charges. Protons have a positive charge, electrons have an opposite negative charge. Neutrons are kind of in the middle, they don't have a charge at all. In terms of a mass, protons and neutrons have an equal mass to one another. These are measured in atomic mass units, which is a really small unit of measurement, obviously way smaller than a gram. Electrons are really much smaller, to the point that we don't count them at all in the mass. And then finally, in terms of a location, the proton and the neutron are both found inside the nucleus of the atom, and the electrons are found outside of this in the electron cloud. So effectively, if you look at this, the protons and neutrons are very similar to one another. They're both in the same place, they're both the same size. The way that they differ is in one has a charge, a positive charge, and one doesn't. One of the things I mentioned in my understanding of this, the function really of the neutron, if you think about it, is it allows a bunch of positive charges to stay together in one place. So there's a force that acts between the neutron and the proton that kind of allows them to be clumped and hold together. Electrons are different in every regard. You'll notice there's a difference in charge, there's a difference in size, there's a difference in location. So if we sketched out just kind of a rough drawing of things, we might have a nucleus on the inside where we'll say these solid dots are protons and these open areas are neutrons, and then we would have an areas around the atom, and this is where we would find electrons. So this is, again, a basic understanding. As you go through high school chemistry, college, you'll get more and more complete understandings, hopefully, of how this stuff is put together and our basic understanding of it. So if we look around the world, what we know is that there's a lot of varieties of these atoms. They come in a lot of different versions of one another. So things that we can change up, we can actually change up all of these things. So atoms can have different numbers of protons, they can have different numbers of neutrons, and they can have different numbers of electrons. By far the most important of these is the proton. And I guess when I say important, I mean, I guess in terms of if we change a proton of what happens to the particular atom that we have. So the importance of the proton is that the proton number determines the element that we're working with. The elements are all the things we find on the periodic table: gold, oxygen, lead, and these are, again, the fundamental building blocks of nature. And these are made of atoms as well, but the idea is that an atom of gold is different than an atom of oxygen, and it's different than an atom of lead. So one of the fundamental ways that they're going to be different from one another is that they're going to be different in their number of protons. So every element differs in the number of protons they have. So if we had an element that had one proton, which actually would be hydrogen, and we added another proton to it, it's no longer going to be called hydrogen. It becomes something totally different. It becomes helium, because that's basically how we define helium. It would be the element that has two protons to it. If we added a third proton, then this is no longer helium, it becomes lithium. So as we add protons, it ends up changing the element that we have. Now, if we change, and it's possible to do this as well, we can also change the number of neutrons that an element might have. So for example, hydrogen always has one proton. That's what defines hydrogen. Hydrogen can actually have 0 neutrons, or it could have 1 neutron. It could actually have different numbers than that as well, but we'll just use this as an example. If hydrogen had 0 protons, it's still hydrogen because, if it had 0 neutrons, it's still hydrogen because it has 1 proton. So we could have a version with 1 proton and 0 neutrons. We could have a version with 1 proton and 1 neutron. So since the proton numbers are equal, it's still the same element, which is hydrogen. The neutrons differ, so let's go back and think about the characteristics of neutrons. They don't have a charge, so it doesn't change their charge, but they do have a mass. And so since protons and neutrons have the same mass, if we change the number of neutrons, the result of this is a change in the mass. So for example, this first versus the second one, this one would have a weight of just 1 atomic mass unit because we only have 1 proton and 1 neutron, whereas this one would be twice as massive and would have a mass of 2 atomic mass units. So if we change the neutrons, we can do that, and it happens in nature. The element remains the same, but it just gets a little fatter, or if we took one away, it gets a little skinnier. If we change the number of electrons, let's think about the characteristics of electrons. Electrons, if we change those, well, does it change the mass? No, because electrons effectively don't have a mass. Does it change the identity of the element? No, it doesn't do that either. The only thing that the electron really brings to the table is a charge. And so if we add or remove electrons, then what we're going to be doing is changing the charge of the atom. So very often what we'll say is that the number of protons, so for example with oxygen, if oxygen has 8 protons, we would say that it has 8 electrons. That's going to be true if this is a neutral atom. In a neutral atom, the protons and electrons balance out because these are positive and those are negative. Okay. So if we did something with the electron number over here, for example, if we added a couple of electrons, and again, this is something that might happen in nature because electrons can hop on and off of atoms, but just as a hypothetical example right here, if we turned our 8 electrons, say, into 10 electrons, then now what happens is we don't have an equal number of charges. So it's not equal anymore. There's actually more negative charges than there are positive charges. Okay, is this still the same element? Yeah, it's still the same element because we haven't changed the protons. Is it still the same weight? It is, because we haven't changed either a proton or a neutron. The only thing that's changed is an electron, and since electrons really just have charge, that's all that's changed. We've added 2 negatives, and so this now has an added charge of -2. So we can add and move these things around, but there's kind of a consequence for changing any of these items that we might have on there. So again, the big thing to keep in mind though is that the proton is what ends up defining the element that we have. And so that's why when we go to the periodic table has some numbers in them. And if you look at the periodic table and read it like a book, it goes 1, 2, 3, 4, 5, 6, 7, 8, and so on. And as we look at the numbers that we have in here, every element has a number at the top, and this is our atomic number. That number is the number of protons for that particular element, because remember, we can't change the proton number. And then we'll have a symbol here, and then there's a number on the bottom, and this is our average mass. Now the reason it's an average mass kind of goes back to what I was showing with hydrogen. Remember hydrogen? Hydrogen can have a situation where there's 1 proton and 0 neutrons, and we might have a hydrogen that has 1 proton and 1 neutron. Well, the mass of this one is 1, the mass of this one is 2. This one's a lot more common. There's way more ones. Like for every 1, excuse me, it would take lots and lots and lots of 1s if these are all hydrogens, and then there's an occasional 2. If we average all these numbers around, I know they're messy. If we average all these around, it's not going to be 1.5. It's not going to be just 1 and 2. We got a lot of 1s. And so the average for this might be really close to 1. So in fact, it's so close to 1, we might just say, well, the mass is normally 1. But there's an occasional 2, which is going to increase the average just a little bit. So that's why we see this number as usually a decimal number. Rule of thumb is that usually if we round this number, it tells us what is the most common form of that particular element. So for example, with hydrogen, the number on our periodic table is 1.01. That lets us kind of indicates that probably the most common version of hydrogen is this one. Okay. If this was the more common one, then the average number should be closer to 2. And so again, we can change the number of neutrons around, but we can get lots of information from the box we have here. Okay. So if we have examples of things where we're trying to figure out how many protons, how many neutrons, how many electrons something has, and we want to go to the box, and if we take something like oxygen, and oxygen has an 8 at the top and it has a 15.99 at the bottom. So if we wanted to know how many protons, electrons, and neutrons does it have, remember this top number tells us the number of protons, so it would have 8. If this is a neutral atom, then the pluses are going to equal the minuses. So then we would also know that the number of electrons would also be 8 if it's neutral. So it kind of tells us both of these things. Now this number, again, remember, this is our average mass, so if we round this, we could round this to 16. That means there's a total of 16 protons and neutrons added together. Okay, so I'm kind of getting messy here, but that means, all right, so protons and neutrons equals 16. Well, we've already determined, right, that 8 of these are protons. So 8 plus what is 16? 8 plus 8 is 16. So we would know that there's 8 neutrons as well. Another rule of thumb is if you take the mass number and you subtract the atomic number, that's going to tell us the number of neutrons. Okay. Why does that work out? Because the mass number is protons and neutrons together. The atomic number is simply the protons. So if we subtract, what happens? Those are going to cancel out, and we end up just with the neutrons down at the bottom. All right, so the last little piece we went over is electrons and the electron shells, because electrons, because they have a negative charge, they tend to have to be spread out from one another a little bit. And so what we said was that electrons travel around in orbitals, and these orbitals are of varying sizes. And we can also think of them as shells, like around the outside of the nucleus. So if we have a nucleus, there's various shells that we could think of that would surround it and make a big circle all the way around, if you want to think of it this way. As we go through these, each of these shells can only hold a certain number of electrons. So our rule of thumb is that the first one can hold 2, the next one can hold 8, the third one can hold 8, the next one can hold 18, and for the sake of our class, we don't really go beyond this. So in addition to using the periodic table to figure out how many electrons it has, we should also be able to figure out how many electrons should be in each shell. Again, our rule is you have to fill in the first shell before you can move to the next shell. So if we go back to something like oxygen, where we said that oxygen has 8 electrons, of those 8, we have to actually divide them up. So oxygen would have 2 electrons in the first shell, and then its remaining 6 would end up being in this next shell. What about the third and fourth shell? Well, for oxygen, they basically don't exist because it doesn't have that many electrons in it. Okay, so as we figure out how many electrons it has, then we can figure out where they go. Another rule that we say here is that atoms don't like to have partially full rows, shells, however you want to think of it. Okay, We don't like to have partially full shells. So what happens in reality is that atoms will either gain or lose electrons to make sure that this doesn't happen. Now, when will they gain electrons? They're going to gain an electron in a situation like this. They're going to gain if it's almost full. So in the case of oxygen, for an example, if this were the case, it might want to try to add enough to turn this 6 into 8. So what would it want to do? It would end up adding 2 electrons so that it fills up this last little shell. Now, what's the consequence of that? These electrons bring a negative charge with them. So if they gain, they're going to gain when they're almost full. That's going to make the atom become negative, and we use the word ion to refer to that. If, on the other hand, we had something like lithium, lithium has 3 electrons, so it would have 2 electrons in its first shell, and it would only have 1 electron in its last shell. So what's going to happen here is it's going to lose this electron because it's not almost full, it's almost empty. And so the easiest way we can get rid of a partially full shell like this is just to get rid of this 1 electron. So it's going to lose its electron or electrons if the shell is almost empty, and if it loses its negative charge, then it actually becomes a positively charged ion. So in this case, this would go away for lithium, and then lithium would end up having a +1 charge when that happened. We'll work more on this next week. The other idea with the electrons is that this electron arrangement, this 2, 8, 8, 18, with the electrons is very much the reason why the periodic table is shaped the way that it is. If we look at the periodic table has, there's a box over here and a box over here. That is our first row, which has only 2 things in it. So there's 2 boxes in the first row, and that's because the first electron shell can hold only 2 electrons. Hydrogen has 1 electron, and then this one has 2. So once we get to this column, our electron's shell is full, and then we need to go to the next shell. The next shell is actually the next row in the periodic table. The next row in the periodic table has 8 items on it. So let's see if I can not mess this up. 3, 4, 6. Okay. So the first row has 2. The first shell has 2. The second row has 8. The second shell has 8. So think about what we're doing if we were filling in electrons. Each box, I'm going to put a number in here, and this is how many electrons that this one would have. So the third electron would be here, the fourth, 5th, 6th, 7, 8, 9, 10. So when we get to the end here, again, we've got 10 electrons. So we've got 2 in the first shell and we've got 8 in the second shell. So basically at this point, at the end of the row, we have filled up our second shell, which is why we have to go to the next row in the periodic table. It also has 8, and our third shell has 8. And so we would fill in these again to get to the very end. Once we get to the end of this is where we would have 18 electrons, so 2, 10, 18. So we'd have 2, 8, and 8. Once we get to this element here, which is argon, again, argon has all of its shells full. So then if we go to the next element back at the beginning of the next row, we have to start on our 4th shell. So there is a relationship between the shells and the rows. Okay, so everything in the first row has 1 shell, everything in the second row has 2 shells, everything in the third row has 3 shells, and so on. And one very last thing about how things are written sometimes. Sometimes we will write our elements with a number after them, like carbon 12. This number at the end is the mass. And remember that there's no reason for this to be the atomic number because carbon always has the same atomic number. So try to keep in mind these elements can come in different versions of one another. And so we need to be able to specify each version. So carbon 12 is a particular version of carbon. There's also a carbon that's called carbon 14. Now, how are they similar? They both have 6 protons. Now, again, how in the world would we know that? Well, the periodic table for carbon has a 6 at the top. And remember, by definition, that 6 is the atomic number, which tells us the number of protons. So no matter what version of carbon we have, it's going to have 6 protons. So what's different between these two is that they have different masses. Well, the only things that have mass are protons and neutrons. Well, we've already indicated that they have the same number of protons, so it can't be the protons that's causing them to weigh anything different. So that leaves the neutrons as being the only thing left. So the idea is that carbon-14 would have 2 more neutrons than carbon-12. Okay, so carbon-12 would be 6 protons and 6 neutrons. That adds up to 12. Carbon-14 would be 6 protons and 8 neutrons. That's going to add up to 14. So sometimes we'll see it written like carbon-12. It could be shortened to the symbol. We could have like C12 or C14. Sometimes it might be written with a carbon and then the number is up here at the top like this. So anytime you see a name or a symbol with a number, that number is generally going to be the mass number that we need to use to do our calculations with.